let me know if...
Yeah, that looks great.
Perfect. So thank you so much. First of all, a big thanks to the organizers for having me here. It's really a great pleasure, and I would like to give you a little bit more of insights on the behind the scene of the work that we have been doing in the last 2 years. So the talk will be basically the chat, the discussion will be focused mostly around the design of a core component based on natural language processing. So there will be many details for which I will just run quickly through them. And if you have questions, feel free to post them also in the chat. Depending on time, I will be happy to follow up with you even there or in person. So let's start first and foremost by introducing the team that is behind this project. I may use the I, the first person, referring to myself when I'm talking about some of the implementations, but please consider all the people that you see here. Without their effort, the work would have really not been possible. We started this activity, the activity of combining machine learning and automation hardware in chemical laboratories for organic synthesis in 2019, at the end, towards the end of 2019. What we had in mind was to design a system that was running in the cloud, so wherever there is an internet connection available, that may have been used by people to draw a molecule of interest, and then with a series of data-driven models, so machine learning models, the user was actually driven through the design of the synthesis as an initial step, and then as a second step, executing the synthesis designed on automation hardware. And for doing that, of course, there was an important piece that was actually missing, that is the conversion of chemical reactions schema, so chemical reaction representation, into a sequence of operations that make up the procedure to execute that reaction step. We also conceived a way to monitor remotely the chemical synthesis and to intervene with the chemical synthesis. So this, in essence, is the entire project. We called it RoboRxN from Rxn. All the models that I will be briefly describing are actually publicly available, including also the use of the platform. So if you are curious, feel free to give it a try. The very first thing is that we started really by the principle, given a target molecule, we wanted really to design a specific synthesis. And for doing that, we had, of course, to rely on some data. I will give you in the next slides a little bit more of information on the type of data that we have been using. Compared to chemical companies, IBM didn't really rely on an extensive data set of chemical reactions, not being chemistry really the primary business of the company. So we had to really experiment a lot with sources of data that were publicly available. And so the general concept is that you want to go from a target molecule into that molecule in a vial, so physical synthesis of that molecule. And the very first step in doing so is, of course, the retrosynthetic analysis, the retrosynthesis. We have been doing that in a way that uses language models, and I will just give you a very quick overview of that means, but basically I don't have to reinstate, I mean, the importance in this audience, the importance of a retrosynthetic analysis and the role that it has in the synthesis. For most of the purposes here is important only to know that we have been constructing using an approach in which we treat chemistry as a language and combining that approach with an hypergraph exploration, where we are expanding on the fly the entire construction of the retrosynthesis and then optimizing the routes. The second step is actually the one of converting a synthesis or a retrosynthesis into a sequence of operation. Still today, this is one of the steps where in combining machine learning with automation hardware, you need a firm presence of human experts in really deciding the correct sequence of operations and parameter for executing a synthesis. And so this was the space in which we tried really to explore the use of natural language processing and capturing the signal presence in published experimental procedure for chemical synthesis in order to build a model that receives as an input a chemical reaction and is producing as an output a protocol, an experimental recipe for the implementation of that synthesis. The rest of the talk will be really focusing exactly on the technical details of this part. So the core, to a certain extent, the brain of the entire technology. The last part is actually the execution on a robotic system. There, we decided to take a very pragmatic approach. We didn't construct any custom hardware. We decided really to follow a way where all the data-driven layers were actually combined with commercially available hardware. And so we really decided to pick up one vendor and build the entire infrastructure in the cloud in a way that is as much as possible hardware agnostic and that allows in the future the combination of different type of automation system. So altogether, basically, these are the three components: the retrosynthesis, the action, the execution. I will also bring this in the upper part, right top part of the screen. And I will give you a little bit more of details in all of them. So the very first part is actually the retrosynthesis. As I said, one of the major goal is, of course, determining the entire sequence of operations that may lead to the synthesis of a target compound. And in doing so, we have been starting from an easier problem. The easier problem that we tried to tackle at the beginning is actually the forward reaction prediction. Now, in a context, in a chemical context, the forward reaction prediction and the retrosynthetic analysis can be considered like two operators, one the inverse of the other. And we try to tackle this problem, the problem of the forward prediction first, because compared to the retrosynthesis as all the peculiarity of a function. So is one very well-defined problem that mathematically can be casted as a function. Like instead, the retrosynthesis per se is more a relation between the set of the precursors and the set of the products. How did we tackle the forward reaction prediction? Here, it's really the essence of the entire data-driven technology that there is behind the work that we have been doing the last 3 years. We have been, first of all, relying on a textual representation. We have been using smiles. There are many interesting reasons why smiles, for instance, perform better than even more modern linguistic representation for molecules. They are very simple. They have a very codified grammar, and in their simplicity, even if it's quite difficult for humans to write directly smiles, like we draw molecules on the blackboard, but in their simplicity, they make the task to natural language architecture of learning the underlying grammar very easy. What does it really mean to treat chemistry as a language? It means that we can imagine that predicting the result of a forward reaction where we have reactants, reagents, and we want to predict the product is nothing more than a translation between a language of the precursors into a language of the products. So it's like having two different languages. One could be equivalent to English, the other one could be equivalent to my mother language, Italian, and you are actually constructing a translation architecture between English and Italian. And the way to do that, the way all the neuronal machine translation architecture that translate between languages, like Google Translate, for instance, is the way they are developed is actually incredibly simple. You need to have a huge list of sentences in language 1 and correspondingly translated in language 2, and you are constantly training the sequence-to-sequence model. This is another name for neuronal machine translation architecture, by showing the sentence in English with the corresponding sentence in Italian. And by doing that across many epochs, the architecture is actually capturing several information. In the specific, is capturing the grammar of English, is capturing the grammar of Italian, but it's also capturing how the words in English and Italian are mapped to each other, including also the corresponding position. And this mapping is actually equivalent in the context of chemical reaction to determining how the atoms from the precursors are actually mapped into the product. So how does it really work? Then the training of a forward prediction model, you need to have a very large number of chemical reaction. We extracted the chemical reaction from patents, and we represented this chemical reaction as a token in which each letter is actually, each element, each token for each element is representing a word, and all the words together are making up the sentence in that language. So we tested different architecture, and then in 2018, we consolidated on the use of the transformer. And still to date, the transformer are among actually the architectures that are providing the best performance between data-driven models for forward reaction prediction with more than 90% accuracy. So that's the forward reaction. The retrosynthesis itself is simply the inversion. So here, constructing a model for a single-step retrosynthesis is as simple as inverting the order of the languages. So there is very little work that we had to do. Most of the work was actually placed into the construction and the exploration of the retrosynthetic tree. So now the next problem is actually the second one, and here I want to dedicate a little bit more of time. Now we have, let's imagine that by using the transformer and the hypergraph exploration, and by having the concept of a human intervening on the prediction of the machine learning model, you have a sequence of steps that are determining a possible synthesis for your target molecule. So the next question was, how do we systematically scale the execution of this synthesis on a commercial automation hardware? And we did that by looking at the problem of predicting the action in a very similar way to determining the forward reaction prediction. We are still using a translation architecture. We are using a BERT model belonging to the same family of the transformer architecture for actually connecting chemical equation with the corresponding published experimental protocols. And so there is a reason why some of these execution are actually quite complicated. I mean, even by changing functional group and maintaining reactions that are very similar, the corresponding recipes may actually be very different. The introduction of a functional group may induce the requirement of having phase separation rather than filtration because of solubility problems that are introduced by the presence of specific functional group. Therefore, even the use of same templates for procedure is actually of very limited use. It's not always applicable and requires a little bit of extension. In general, it's a very hard topic. It's a very hard problem to predict the exact execution, and I will give a little bit more of detail also on the performance that we managed to achieve using a public data set of experimental procedure. And as I mentioned, ideally, we want to follow a very similar translation approach. We wanted to follow a very similar translation approach to the one of the forward prediction, but in this case, translating from a reactions miles, so precursors that go into a product mapped into the corresponding sequence of actions. Now, the very first thing that the very first problem that we had to tackle, and this was not really a small one, and is the #1 problem when you want to try to embed data-driven solution in your project, is the availability of a useful data set. And while, for instance, for the forward reaction prediction and the retrosynthesis, we have been relying on publicly available data sets like the USPTO work by Daniel Lowy, or even commercial one like Pistachio. For the recipe, the situation was completely different. There was no standardized, curated data set of experimental procedures. So we were really looking for having a large number of paragraphs made up of sentences like the one that you can see on the left side of this chart that is actually converted into a specific function. And that specific function that at the end will be the function executed on the hardware is actually translated with a sequence of actions. What we did was exactly the construction of the model that if you are curious of more details, feel free to ask questions. I'm more than happy to talk about the details of this model for building the data set, but all the details are also available into the publication reported at the bottom of the slide. But in summary, one of the take-home messages is that we managed first to map all the corresponding procedures and protocol with 13 or 14 actions. So we really restricted the entire mapping of the chemical reaction only to 13, 14 actions. We also built initially a rule-based model for annotating the paragraph and extracting the actions. And then what we did, we used the rule-based model for pre-annotating the text, curating by humans with a round of annotations, and then building a deep learning model for the conversion of paragraph into actions. Again, this is a technology that is available. You can download the models, but you can also use directly the model themselves on the RxN portal if you are curious to know how that is performing. So the result of this operation is actually a data set of many reactions that are mapped into many experimental protocols in which we have gotten rid of all the textual descriptor, the human readability, and we have really condensed the entire procedure into coin-size steps, sequences of operations. And what we did was constructing a transformer model that receives in input each individual reaction smiles, so all the precursors that go into the product, and that is trained for translating the corresponding reaction smiles into the corresponding operations required for executing that reaction step. Now, what does that really mean in practice? It means that, and this was also, I'll take a second of pause just to think a little bit of the complexity that there is behind this operation. What you try to do when you try to create a relationship between structural features with the use of a reaction smile and the corresponding operation is trying to find a functional dependence between the presence of specific groups with the presence of specific operation. Now, you can imagine that the slight modification of the chemical scaffold may induce profound modifications into the sequence of operations, from temperature, but even to physical operation. We mentioned before the solubility or the precipitation, phase separation, and so on. And this was really one of the greatest doubt that we had till the very end. The reality is that it's clear to everybody that there are physical laws that are governing the solubility and how molecules are reacting in solution, the temperature that are directly related to the activation energy. But what you try to do with this model is capture all these quantities and map them into a sequence of operations. Now, there is a signal, but the signal is like incredibly weak. It's like having a signal that is more or less immersed into the noise. And so we have been wondering until the very end whether the collection of procedures that we managed to extract from public documents, patents, was actually sufficient for averaging out the noise and learn really the signal between structure, relationship, and procedure steps. So overall, we managed to have 700,000 protocols that we have been, this is actually another interesting topic of discussion. We started initially with 10 million entries. And after eliminating duplicates and doing some consistency check at the level of statistical analysis, no human curation protocol in place, we managed to reduce the set of 10 million experimental protocols extracted from patents to 700,000 entries. So basically we retained 7% of the original data set. And we are definitely not in the position of swearing that the 700,000 are actually error-free. So the only thing that we managed to do is really to remove as much as possible all the evident bias that is capturable by statistical analysis. But definitely there will be procedures that are inconsistent, that provide conditions that are completely wrong. However, what we managed to see is that on average, the prediction of the model is better than the worst entries in the dataset. This is really the one of the great things about data-driven modelings. So you can easily average out, as long as you have a sufficient statistically good distribution of your experimental procedures, you can average out really those errors that are non-systematic, that are appearing, that are very difficult to eliminate, like for instance, recommending the use of water as a solvent for a green yard. This is really only one example. You can easily average out this information by using the fact that all the other procedures describing green yard are actually not relying on water. So this is in essence also the SMILES 2 actions. You have a chemical reaction prediction that we represent again in a linguistic form as a SMILE, reaction SMILE. You have the corresponding operation, the corresponding recipes, and we train the model by giving in input the reaction SMILES and by training the model to reconstruct this experimental recipe. And this, of course, was then generalized. This protocol was generalized in order to be more easily understood by the model and also more easily generalizable depending on the individual molecular scaffolds. So all that, the step from reaction SMILE to the corresponding actions that are executed in the automation hardware are entirely predicted by machine learning. So here there are exactly the same information that I had before, just with a little bit more of details. Again, 700,000 is the data set that we have been using. We started initially from 10 million entries, but they were reduced after duplication to removal of duplication across all the different patents to almost 3.5 million. And again, statistical purging was actually bringing the data set down to 700,000. The last part, so this is actually the core of the entire technology. The last part is really the execution of the chemical robot. So I will be closing very quickly in case there are questions. The general idea is that now for every single reaction of the synthesis plan, you are capable of generating specific actions that can be executed on the robot. And so the way we constructed the entire layout, there was a lot of software engineering. And I must say that even if this was the part less data-driven, probably, was definitely not the least interesting. I mean, there have been so many designs and discoveries that we did on how to use at best cloud technologies for scaling up the entire use of that, not only to a single instance in one laboratory, but actually ideally even to a large number of automation systems hosted across the globe. And so the way everything is working at the moment is actually with all the components, all the machine learning, but even all the software that is controlling the execution of the robot living in the cloud somewhere between Europe and the United States. In the cloud, we have, of course, what you experience when you connect to the website. There is the broker for deciding actually on the action, the controller that takes the lead for the entire execution on the AI workers, and then the scheduler that is really taking care of the best use of the automation hardware that normally, at least in the layout that we have, is residing behind the firewall, not easily, not publicly accessible. Even there are very interesting mechanisms for guaranteeing the security of the hardware. by still providing virtual access to the platform to the users. And so everything here on the hardware side is living on the edge or behind firewall, and everything here is actually the components that are publicly available. So if you are interested, really feel free to have a look at the website. There are all the models that I showed. Few words about the automation hardware. Again, we decided to go for one specific vendor, mostly because of the geographical vicinity and the fact that there were some solution for which were actually matching exactly the type of chemistry that we wanted to automatize. And so we went for batch reactors, 100 milliliters. So this gives you also an idea of the scale in terms of mass of synthesis that you can do. There is the possibility to handle liquids. We also went for a very alternative way of handling solid by encapsulating them into glass pills of 50 microns thickness, and by using pressure for actually the activation of the glass pills inside the reactor. So that's the system. Originally, we had mounted to the system, we wanted to have a feedback mechanism. So originally we connected the automation hardware with an LCMS. So this is an high resolution TOF. And for, I would say, quite a few months, more than 1 year, we have been operating this prototype lab only with the use of the LCMS. A few months ago, we coupled an additional instrument. This is a benchtop NMR, 80 megahertz for complementing the analysis. So basically, from a user perspective, whenever you are executing synthesis on the web from the web browser, you have the possibility to trigger analysis during the synthesis execution. You have the possibility to collect the analysis of the instruments, and there is the potential to also use the analysis for having feedback loops on the decision of the execution of the chemical synthesis. So stopping the chemical synthesis or maybe initiating new routes. This is in short, it's like a 30 seconds video that we recorded. We are streaming more or less 24 hours during activity, during inactivity of the lab. This is just a recording that shows you all the camera. We constructed like a sort of big brother to have full control, full view of what is happening on the platform remotely. So it gives you a little bit of idea of what you can experience on this platform remotely. So I'm more than happy if you are interested to share the slides. They are public. There will be some links. If you are curious a little bit more into the details of the machine learning part, the data, there is a GitHub repository where you can download the public data that we reprocessed and at the same time the model. And so I'm stopping here and actually thanking you all for the attention.
Thank you, Tier. So I know we have a question.
I can probably.
Yeah, we'll start off with the question in the chat. From Benji, how do you work with functions that have multiple solutions, especially for the retro synthesis?
Yeah, exactly. So this is actually the problem that I was referring to very quickly at the beginning. We started with the forward reaction because they are really very well-defined functions in general, but the retrosynthesis itself is not, you can't really frame it as as a function. It's really more a relationship between sets. And is this a major problem? Not really. I mean, it comes with some, in my opinion, very fundamental concerns, especially when you try to rank retrosynthesis, believing that there is necessarily an order in which the hypotheses are generated. So the way we handle this is very simple. You can always keep, and you can do that also for the forward prediction model, by the way. Yeah? So you can abstract from a retrosynthetic perspective and ask the model, the architecture, to give you one prediction, but to give you 2 prediction, 3 prediction, 5 or 10 prediction. And then the major difference, because you can do the same also for the forward prediction model, but the major difference for us is how do you treat these 10 different reactions. The very first thing that we debunked is the use of a confidence score that is directly related to the top N accuracy prediction. The reason is that the top N accuracy prediction is only mimicking what is present in your data set. You are not capable to abstract really the learning that you made out of the set in terms of organic chemistry. So we introduce new metrics, and that's basically how we handle the retrosynthetic predictions. We don't talk about top N prediction, we talk about metrics like round trip accuracy, where you make a prediction with the retro, but at the same time you validate the retro with the forward prediction function. And whether you are going back into your products or not, it's really assessing the round trip accuracy. There are other metrics like the Shannon metrics or the diversity. These are more metrics that are characterizing how well this relationship between sets of precursors and product has been trained. So overall, to be really transparent, there is not a major difference from a structural perspective on how you treat a function or a relationship between sets, but it's more on how you interpret the results.
Great. So we have an in-person question.
Yeah, thank you for your talk. I think a lot of this work has been like really interesting. I guess a quick follow-up on the previous question. I guess, do you find like efficiency to be a problem when you're looking at multiple retrosynthetic routes, just from the computational standpoint? And is there any way you address that?
Mm-hmm. Efficiency, I guess you refer really to time to solution, or efficiency in terms of confidence of the prediction of the model?
I guess both would,
mm-hmm.
you know.
Okay, yeah, I can comment a little bit on both. We can start with the time to solution. So computational efficiency. Clearly, it's about the exploration of a tree. So we put in place, I mean, a mechanism for exploring hypertree tree. These are really very, very fine details, but to explore tree, and of course, I mean, you can imagine that the computational complexity, if you would be expanding from the target molecule, you would be generating like 10 possible disconnections or 10 possible routes that go back to that product. And then from each of these 10, you would go and do additional 10 expansion and iterate that for 5 or 6, 7, you would end up with a number of possible paths that you should explore, which would be humongous. So what we do, we introduced one metric that is actually, it's a sort of probabilistic score. We were inspired actually by the Bayesian probability to reconstruct a scoring function that has a conditional probability at the numerator, and at the denominator it has something that is not really related to a Bayesian probability, but has to do with the simplicity of the molecules that are generated by the retrosynthetic analysis. Now, the interesting thing is that although there is no specific proof, this function is actually bringing you, we were very surprised to see that this function brings you in this exactly in the same, in the right direction. It basically tells you what is the probability based on the training set that you have been using for training the models, the retrosynthetic model, that the prediction it's actually a good one for synthesizing your molecule. So we use that score for limiting as much as possible the expansion. Every time we do 10 expansion, we use the scoring functions to retain only a small part of the tree, and we keep expanding and refactoring and repruning the entire tree in such a way to keep it streamlined. And this is the reason why evaluating a retrosynthesis event for 10-15 steps at the end, it takes maximum a couple of minutes. Regarding the efficiency in terms of accuracy, so this was the second part of the question. Well, the two parts are a little bit disconnected and depends a lot on how you are evaluating the overall performance of the retro. Now, for instance, there are one of the latest trends is the one of using metrics that are taking into account the entire retrosynthesis instead of focusing on the individual steps. So this is going to be a very interesting topic, because it's true that compared to chemical reaction, we have way less retrosynthesis, so full retrosynthesis that we can use for ranking. But it's also true that this is really the best measure that you can do. If you rely, like we do, only to a single, at the moment, only to a single, the evaluation of a single efficiency, a single performance of a prediction, and then you see the overall performance like a multiplication of the accuracy, then in this case, it's really pretty much independent. You have that, of course, reactions that have confidence, predicted confidence that are very small are having a huge impact. And the only way in the overall score of the retro. But the only way to limit and somehow take care of that is to introduce a metric that consider the ranking of the retro across other existing retros available in such a way to mimic existing synthesis.
Great. We probably have time for one more quick question. Oh, did you have another question, sorry, or a follow-up?
Is this on? Great. So you described your whole approach in terms of recognizing molecules and their products as words. But of course, words themselves only have meaning when taken in context. So in terms of prospectively thinking how to encode the function, what are your thoughts on some form of decoder to kind of pick apart the function in a particular context?
Mm-hmm. No, that's a very interesting question, and maybe I will be. Let me know if my answer actually is matching your question. But let me give a couple of considerations. That's absolutely true, and there are. I think we are experimenting a period which is super interesting for chemistry in general, especially when combined with natural language architectures. So there have been some works recently outside of our group, so independent from us, but where they are exploring really unified frameworks where you try really to create that variability in the context by having unified learning schemes depending on different type of tasks. So you don't have necessarily, we suffer, one of the major problems is that if you want to train a translator between English and Italian, very likely you will be handling billions of sentences that are providing sufficient context for understanding the precise equivalent of an English word in Italian, depending on the other context of the English word in the sentence. Now, for chemistry, I'm a strong believer that the situation is very similar. You may have like functional groups that may have a specific meaning because of long-range effects of other functional groups in the molecule, or because of the presence of other reactants. So these are really effects that are non-local. And this is probably one of the greatest advances compared to rule-based system. By definition, rule-based system is something, it's a way where you are focusing the attention on a locality of the information. So the problem, though, is exactly what you mentioned. If you want to capture that relationship, you have to have an extensive data set. And probably 3.5 million of chemical reaction entries may not be really sufficient to capture the entire linguistic complexity of functional groups, structural motifs in organic molecules, and so on. So this is really one of the limiting factors. On the other hand, regarding the decoding, there I can spend a couple of words. I mean, one of the thing that has always been, the concern that has always been raised is that these language models are probably even more than neural networks that are ranking rules, chemical reaction rules, have always been addressed like black box. And to a certain extent, I mean, it's true. I mean, you have like a system that tries to interpolate between different languages. I mean, your representation of precursors, your representation of products, you don't really know what is happening in between. And this was until last year. So what we did, and it took a person that had lots of patience in looking to a multitude of numbers. But what we did, we started looking at the weights of the attention layers. So basically the weights of the decoders in one task that was not the forward direction prediction task, it was a masked language task. And so by looking at those weights, we managed actually to recover that there are specific parts of the attention layers in the architecture that are learning how atoms are mapping between reactants, reagents, and products. So this is a crazy discovery, because technically, in a SMILE, you don't have any atom mapping information. We don't use atom mapping information. So we don't even order the atoms in such a way that the order in the string is actually reflecting the order of the atoms in the string of the product. However, I mean, what the attention is focusing is capable of reconstructing, mapping one atom from one side into another one. So there is a lot, in my opinion, that can be discovered on the use of the language models. And this was really just an example. It may not be that simple, clearly, because we talk about architectures that are quite complex, but it's also true that there are so many efforts from in the language community where it's really possible to create lots of parallelism. And to a certain extent, even the discovery that we did about the atom mapping was actually triggered by additional work done in natural languages, so not in chemistry. So there are so many parallelisms that actually are working that allow you to recover from the training of language models physical properties with physical meanings. Atom mapping is one. We applied the same context, for instance, in having enzymatic reaction where you have substrates, you have the entire sequence of amino acids as a catalyst, and then the product. And there you are capable of identifying the amino acids that are interacting with the atom of the substrate. So you are able to recover three-dimensional information from one-dimensional representation. So there is a lot, in my opinion, that one can do on processing that information with functions that have physical meanings.
Thank you so much, Thierry. Unfortunately, we're going to have to end the Q&A there. We're actually scheduled to go to a break. So thank you again for a really great talk and a lot of great questions.